Good afternoon and welcome to the fourth lecture in the ILR. I call it a 3-credit-hour course, if you will, a broad survey class in nuclear weapons and nuclear power, facilitated by Walter Wynn. Walter has prepared a fine series of lectures concerning the history of nuclear fission, including reviewing the atomic structure, the fission process, nuclear bombs, nuclear power plants, and related subjects. And he has an excellent academic and operational background to bring this material to us. And I'm pleased that he asked me to cover the Department of Defense's nuclear power programs, which were given to the Army Nuclear Power Program, part and parcel first of AEC and then DOD, to develop nuclear reactors for shore-based applications. And by way of introduction, I just want to note that I've had several close connections with the early days of our country's development of nuclear power. During 1955, fortuitously, my first tour in the Navy as a Civil Engineer Corps officer was at the submarine base in New London, Connecticut. And the submarine base now is the home to the Submarine Museum, which if any of you are ever up in New England on a vacation tour, stop by Groton, Connecticut and visit the sub-base museum. It's really well done. I became familiar while I was there with the Navy's first 2 nuclear-powered submarines, the Nautilus and the Seawolf, and I was privileged to tour the Nautilus submarine. In 1956, as a member of the base there at New London, I was tasked to develop the first advanced nuclear power course facilities, academic facilities. We converted 2 World War II brick barracks buildings to be the first school that Admiral Rickover had there at New London. And again, fortuitously, after earning my master's in mechanical engineering at Rensselaer Polytechnic Institute in Troy, New York in 1961, I was privileged to be a student in Admiral Rickover's advanced nuclear power course. The advanced nuclear power course at that time basically was considered to be equivalent to a master's degree in nuclear engineering. And I can attest to that because at RPI, I worked hard for a year, but at New London in Rickover's course, I worked a lot harder for 6 months and had about 3 times as many notes on my bookshelf. Well, why and how was I selected for the advanced nuclear power course when I was not one of Rickover's team members makes a real interesting story. But after completing the advanced nuclear power course in December of 1961, I parted company with the Good Admirals program and shifted over to the Army Nuclear Power Program. And this was my opportunity then to become trained as an officer in charge in nuclear power plants general and certified by that program. I reported to the Navy's other nuclear power program. When I say other, I defer to Naval Reactors Program, Rickover's program. This was the one for shore-based nuclear reactor facilities, which was operated out of Fort Belvoir, Virginia, in cooperation with the U.S. Army. And how did the Army come into play with nuclear power plants? Well, let's see if this works. Okay. Within the Atomic Energy Commission were 3 main divisions, the first being the Nuclear Regulatory Commission, and you'll recognize that as being the division that's primarily concerned with the permitting, licensing, operating safely of commercial nuclear power plants. And John Paul sitting up here shaking his head, yes. Oops. Okay. The second division was the Energy Research and Development Administration, ERDA, and during the late 50s and early 60s, the ERDA really evolved into 5 areas of different energy development. The first area was the nuclear weapons development area. The second area was known as NR, naval reactors. And this program was headed initially by Admiral Hyman G. Rickover, which Walter has briefed us so thoroughly about. And the present head is Vice Admiral Frank Caldwell. And this program supports naval propulsion for subsurface and surface vessels. And I talked to Admiral Rickover about 60 years ago, or maybe I should say he talked to me. And I did talk to Vice Admiral Caldwell about 6 weeks ago at a Belvoir nuclear power reunion up in Washington. The third area was the Army nuclear power program, and this was added by Congress in 1954 to accommodate all Department of Defense shore-based nuclear reactor installations. And to a great extent, this is where the AEC got a lot of its early experience that, along with Shippingport, led to the follow-on of commercial power, commercial nuclear power. An existing Army Air Force nuclear energy for propulsion of aircraft program, which later became the aircraft nuclear propulsion. In 1951, it was shifted to the AEC. And then they had responsibility for all their forms of energy, fossil, solar, wind, geothermal, etc. Of course, since this time, the Department of Energy has come into play, and things like nuclear weapons and national laboratories and other things, to a great extent, have found a new home. And the third main division within the AEC was the Energy Resource Council. Okay, U.S. Army Nuclear Power Program. 10 February 1954, the Secretary of Defense assigned the Army the responsibility for developing nuclear power plants to supply heat and electricity at remote and relatively inaccessible military installations. The Secretary of the Army established the Army Nuclear Power Program and assigned it to the Corps of Engineers. And it was really the Department of Defense program, which included the Army, Navy, and Air Force. Today, my focus will be on the Army Nuclear Power Program and the Navy's contribution to it, so to speak. The Army Nuclear Power Program's organization included the Corps of Engineers, which headed it up, and the ANPP's double-hatted presence within AEC, just like NR. Rickover used to write himself letters from the Navy to the AEC and answer them from the AEC to the Navy, which was a very efficient way of getting job done. Also, the Nuclear Power Field Office was established at Fort Belvoir, which was really the major operating arm of the program. And the operational engineering support of 8 early generation nuclear power field plants dispersed from Antarctica to Alaska and Greenland, and 5 DoD research reactors were included in that program. Okay, the Army's Nuclear Power Field Office organization at Fort Belvoir consisted of 3 major elements. First was the SM-1 nuclear power plant. It had a permanent crew, and it had trainees there 24/7, round the clock. And these trainees were basically trained in 4 areas. One was equipment operator, control room operator, health physics, a process control person, and finally a shift supervisor. So the normal component for operating one of these small plants was 4 people, normally all enlisted. And the plant then would have perhaps an officer in charge and a plant superintendent who were officers. The second component of the NPFO was the training department. It was a fairly large department. It consisted of 5 branches: mechanical, electrical, instrumentation, health physics and process control, and a simulator branch. The engineering department, the third major element, was staffed with 75 personnel, and it was composed as a grid-like organization, the project managers for individual power plants drew their support from the 5 technical disciplines: nuclear, electrical, mechanical, chemistry, and systems. And when I say grid-like, I mean the Army officer, or Navy and Air Force officer too, managers cut across the organization, and the technical disciplines, the functional disciplines, they could talk to all of them and get a completed job, get a completed picture of what they were doing. Okay, at the same time, historically, the Navy's Bureau of Yards and Docks stood up the Naval Nuclear Power Unit, NNPU, to operate and support the naval component of the nuclear shore power plants. The unit was established at Fort Belvoir. Its physical building was located adjacent to the SM-1 nuclear power plant, and it consisted of an officer in charge, and all the rest of the people were either Civil Engineer Corps officers of the Navy, or CB, enlisted personnel, or hospital corpsmen. And the hospital corpsmen were trained in the chemistry area, both for hot and cold chemistry and health physics. The unit cooperated with the Army Nuclear Power Program to train and deploy crews for 2 nuclear reactors, supporting the National Science Foundation's United States Antarctic Research Project in Antarctica. The PM-3A at McMurdo Sound was built and successfully operated by the Navy. The PM-2B, planned for an Antarctic snow tunnel installation, was canceled during the design stage when the National Science Foundation's Bird Station mission was curtailed. The unit also held the license for about 70 radioisotope thermoelectric generators utilized by various parts of the Navy. I had the privilege of successfully being the officer in charge of the nuclear power plant, the PM-3A, that we had in Antarctica at McMurdo Station. And then right after that, brought back to Fort Belvoir and was the officer in charge of the Naval Power Program for another couple of years. Also within the Army Nuclear Power Program, in addition to my OIC training, I had 2 permanent jobs with the Army, so to speak. The first one was with the, going the laser here. Oops, did I do that? Okay, the first job I had in the Army lasted 6 months, and it was as the chief of the mechanical section or branch of the training department. And I got a lot of experience preparing lesson plans, teaching, that sort of thing. And that was one of the things that attracted me to UF when I retired from the Navy. And then just before I went to Antarctica and trained my crew in the final stages, I was the deputy director of the engineering department, that 75-person department that supported all of the DoD shore reactors and research reactors. Okay. Okay. This slide shows the 8 Army nuclear power plants in the order of initial criticality, which extended from April 1957 to January 1967. You'll notice, for instance, that there was 1 boiling water reactor, 1 gas-cooled reactor, and all the rest were PWRs, pressurized water reactors, which is what the Nautilus was and what the Navy uses for nuclear propulsion today. And our locations were the training plant in Fort Belvoir, Virginia, an experimental plant in Arco, Idaho, the ice cap in Greenland, a plant that didn't have a home, but it was somewhat tested at Fort Belvoir, the Air Force plant at Sundance, Wyoming, the Antarctic plant at McMurdo Sound, Antarctica, and the SM-1A Army plant in Fort Greely, Alaska. And then finally, a barge-mounted plant that served in the Panama Canal Zone. You'll notice that the first letter of these plants was either S, M, or P, stationary, mobile, or portable nomenclature. The second letter, H, M, or L, high, medium, or low power, and the digit, the plant sequence number, and the third letter indicates its field installation. These 8 plants actually had 4 design sources. The SL1 was designed by the Argonne National Laboratory, and it was really an experimental plant. Where am I here? The ML1 was designed by Aerojet General and was tested for a few hundred hours and then abandoned as a project. 3 of the plants, the SM1, the PM2A, and the SM1A, were designed and built by the American Locomotive Company in Schenectady, New York. Now, if a locomotive company building a nuclear power plant sounds odd to you, you have to go back in history. In World War II, the American Locomotive Company was taken over by the government, so to speak, and directed to develop Sherman tanks and build Sherman tanks for the war effort. And it did. After the war, it got back into the steam locomotive business, but diesels had taken over. And General Motors had been allowed to develop the diesel locomotives during the war. So Alco basically lost their niche. They tried to do other things. Build small nuclear power plants was one of them. Finally, the company staved off bankruptcy by being sold to Alice Chalmers. But it was a big hit to my hometown. Okay, the second design agent was the Martin Company, later the Martin Marietta Company of Baltimore, Maryland, and they built and designed the PM1, the Air Force plant, the PM3A, the Navy plant, and the MH1A, the Army's barge plant that went to the Panama Canal. This slide shows the Army Nuclear Power Program nuclear power plant timelines from 1954 to 1975. And we can see that the ANPP was alive and well roughly from the mid-50s to the mid-70s. So my activity was in the 60s, so I'm looking back 60, 65 years with this talk, if you will. But that was really the country's beginning of nuclear power. And John Paul was telling me Florida Power and Light's plant came online, what, in mid-60s? 65, you see. So how relevant we were to the nation's data recovery, so to speak, on how to best get into this new program. The blue box on this slide indicates the time from each plant's initial criticality to its operational shutdown. These plants had fairly short lives, but we were a solution running around looking for a problem, if you will. I completed Admiral Rickover's Advanced Nuclear Power course in December of 1961, while the PM3A was being assembled in Antarctica by the first crew operating under the direction of the Martin Company. And I joined the Naval Nuclear Power Unit for my officer in charge training before the PM3A first went critical. I was programmed to be the PM3A officer in charge for Crew 3 and winter over in Antarctica, 1963, 1964. When the PM2B contract with ALCO was canceled by the AEC, its prospective Navy OIC was just reprogrammed to be Crew 3 PM3A OIC. This slipped me for a year. Fortuitously, then, that gave me the time to rejoin the Army Nuclear Power Program as Deputy Director of the Engineering Department and to really enhance my career as an engineer. Okay. Another thing, during the period about late 63, I did make a trip to Antarctica and was able to get site orientation with the plant for about 3 weeks before I brought my crew to the plant the following year. Okay. 3 basic nuclear power plant schematics are shown on this slide. Boiling water reactors, gas-cooled reactors, and pressurized water or liquid metal cooled reactors. The boiling water reactor up here, the reactor in all 3 of these is this schematic item. The turbine generator is this schematic item, a pump, and a heat exchanger. And for the boiling water reactor, the primary working fluid leaves the reactor up here as steam, and it goes directly to the turbine generator, and the steam is exhausted and condensed to water before it's pumped directly back to the reactor to be cycled through the primary system again. Boiling water reactors only had one, had one loop. And in the early days, this was really not the best way to go. The gas-cooled reactor was very similar. It had one loop, and the gas exited the reactor after being heated, went through a turbine generator, maybe through a heat exchanger and back through a compressor, and it was recompressed and went around the cycle again. The shaft and the turbine generator operated both the compressor and the turbine generator. So both of these were considered one-loop closed cycles, but the prominent schematic in those days was the pressurized water reactor, where the primary coolant, normally water, very pure water, entered the reactor, was heated up several hundred degrees, exited, and went to a steam generator. Here, the water had its heat removed to some extent and was used to make steam on the shell side of the steam generator. And the water then was pumped back through the reactor. So this was a very small primary closed loop. And this facilitated building that part of a nuclear power plant inside of a containment vessel, which could contain a maximum credible accident should the nuclear reactor have a excursion. Then the secondary loop had water enter the steam generator, the shell side, turned into steam. The steam was used to generate electricity, and it was exhausted from the turbine at low pressure back to a condenser or heat exchanger of sorts. Cool water was run through the tubes and condensed the steam, changed into water, and was pumped again through the system to be converted back into steam. The primary systems were normally operated at a fairly high pressure. My Antarctic experience was with 600 pounds plus or minus pressure in the primary system. The Florida Power and Light plant that John Paul was associated with operated at over 1,000 pounds pressure. The steam side, yeah. Oh, the steam side. What the primary? That was the steam drum. But what pressure was the primary system under? You don't know. Okay, well, I'll stick to my plant then. At 600 degrees, at 600 pounds per square inch gauge, the boiling pressure for water, the boiling temperature for water is 489 degrees. So as long as we kept water under 600 pounds pressure, it wouldn't boil in the loop until it got above 489 degrees. So we operated the primary system at about 460 degrees. So the water coming out of the hot side of the reactor, 460 degrees. So here we were creating steam on the shell side of the steam generator with 460 degree water entering the tubes. So you can see how the two systems interrelated and transferred their heat. Okay. Early on, the pressurized water reactor arrangement was the safest way to design, since it allowed the primary system, as I mentioned, to be isolated and to be built within a containment structure. In closing, we'll briefly look at each of the Army nuclear power plant plants before I turn the program back to Walter, who's going to cover a few advanced concepts. Okay, the SM-1 was the Army nuclear power plant at Fort Belvoir that we all trained on. It was a pressurized water, It was a pressurized water reactor, experimental at the time, used for training. Only 2 megawatts electrical, very small plant, medium in our program. Designed and built by the American Locomotive Products Company. It also included major equipment contributions by General Electric, Westinghouse, and Minneapolis Honeywell. In those days, all the instrumentation was supported with vacuum tubes. Remember when you used to pull the vacuum tubes out of your TV and go to the drugstore and test them? That was the stage that we were at. And the operators were the Department of Defense, the Army, and it had the Navy and Air Force personnel there mainly for training. And a note that the SM-1 reactor provided the very first nuclear power generated in the United States to a commercial grid system, PETCO, around Washington, D.C. It beat Shippingport, the AEC's prototype commercial reactor, by about 4 months. This shows an elevation view of the SM-1. You'll notice in the background is the dome of the containment tank. Over here we have an aerial view of the SM-1. It's 2 stories in this area. The second story was primarily used for offices and training, and the lower level for equipment. Outside the containment tank was a spent fuel swimming pool storage area. And in this building in the middle was a secondary system with a turbine generator set. The SM-1 reactor cutaway looks something like this, and it's important to notice here that the containment tank is designed to maintain all of the energy from the maximum credible accident. This would be the pressure vessel in which the reactor core would be sitting in the bottom. This is a steam generator, and there's a couple pumps in there and a pressurizer. And the steam generator generated steam, and it was led off to the steam turbine and run through the turbine to generate the electricity, and then discharged into a condenser on the bottom, which in this case was cooled by water from the Potomac River, and then as feed water brought back to the primary loop to be reheated, to be brought back to the steam generator to be reconverted into steam. Okay, so all of the primary system was inside this containment tank, and the containment tank was concrete and steel, and should a reactor have an excursion, the core would melt down, and all of the water that it had access to, all the water in the primary system and any other water that it got a hold of, would be converted into steam, and this would greatly increase the pressure inside the containment tank. So the containment tank was designed with concrete and steel to maintain that pressure in there safely. Over here was the swimming pool that the spent fuel box type structures were stored in. And our country is still wrestling with the problem of where to store spent fuel or whether or not to reprocess. These are major national issues still at this point, 60 years later. Okay, oops, forward. Okay, shifting now to the SL-1. This reactor was designed by the Argonne National Laboratory as a boiling water reactor, very small, only 200 kilowatts electrical and twice that and thermal for heating. And the plant was constructed by the Combustion Engineering Company, and they were also contracted to operate the plant, and they were given a crew of operators of Army and Navy Air Force people who were trained at Fort Belvoir. This plant had an unfortunate accident, January 3rd, 1963, where 1 Navy and 2 Army operators were killed. And I had a chance to talk to some of the people who were at this plant, not on duty at the time, but at the plant during this period when the accident happened, that were at my reunion in June. And we'll talk more about this, Walter, next time or time after, about the accidents. Okay, next time. Okay. This is a elevation view of that plant, and you can see that it was in a sort of a sheet metal silo, which is not really a containment vessel, if you will, but it did help contain the accident. And that site today is marked by what to me looks very much like a gravestone. The Army's PM-2A nuclear reactor was built in a snow tunnel in the Greenland ice cap. We had a very strong vested interest, the Army and the Air Force, in Alaska and northern Greenland because of the early warning necessities during the Cold War, watching for Russian bombers coming over the horizon. The reactor type was pressurized water. It was a small 2 megawatt electric plant plus some heating capability again, built by Alco in Schenectady. The construction was by Alco. It was modular, which meant that it was built on skids so that it could be put on a trailer and towed across 100 plus miles of Greenland ice cap. Its location was at Camp Century, Greenland, and it was operational for about 3 years. Interestingly, there was no water, river, or lake nearby to use as cooling water. It was built in a snow tunnel, and they didn't want to use cold air. So they actually developed a bulbous lake down in the ice cap, put steam down there, developed a lake, and then they kept that lake in stability with the rest of the ice cap and used it as a source of cooling water. Here's Greenland, and this is a location at Camp Century. Up in this area, Jack Martin had previously talked to us about his DuLine construction experience. Then here is the snow tunnel, typical, that the plant was built in. These snow tunnels were built by Peter Miller snowing machines, which would drive through at a deeper elevation at each pass through the snow, and it would pick it up whirling rotors in the front and blow it way up in the air and out to the side till they got down to the desired elevation. The problem with this type of construction was that snow and ice is plastic. Ice glaciers flow. Snow is even more plastic than ice. And these snow tunnels, the walls would come in every year and they'd have to be scraped down. And you can see why this was not practical for the long haul. Notice that the construction method was to put steel arches over the top of the tunnel, backfill with some snow. And then this was a very dark home. The ML1 was the Aerojet General gas cycle, and it was not successful in the long run. It was constructed by Aerojet General. It was tested by them, and I saw this plant a number of times at Fort Belvoir when it was being tested. And it was built initially out at the reactor site in Idaho, tested out there. Here's the artist concept. The plant would be mounted on a truck, trailer, and transported along with an army into the field. Now, why do you want a nuclear power plant, say, following Patton's army heading for the Battle of the Bulge? Well, the idea of logistic support, the tail that the Army has for POL, food, ammunition, is hard to keep up with. This power plant was envisioned to be able to draw up beside a lake, generate its electricity through electrolysis, develop hydrogen and oxygen, use the hydrogen from the lake, the electrolysis process, combine it with the nitrogen in the air, of which air is 90% nitrogen, and make ammonia. Use the ammonia as fuel to operate tanks, personnel carriers, trucks, etc. We actually had a couple of pickup trucks running around Fort Belvoir at the time running on ammonia. These pickup trucks just tore up those engines with the ammonia. So it was not practical in the long run. So this whole project was scrubbed. The PM1 reactor was built by Martin, and it was the Air Force reactor in Sundance Air Force Station in Wyoming, up on a mountain. I visited the plant. In fact, I had 3 enlisted men from my crew in Antarctica that were trained on this plant because they were kind of sister plants. And let's take a look at this. Shows the early warning site there on Sundance Mountain, and it shows the nuclear power plant here in the bottom. This was the primary system building. The plant was below the primary system, so to speak, the primary part of the plant, the pressure vessel, steam generator. And this was the secondary building that housed the turbine generator and the feed water skid. And this would be office, little lounge area, perhaps, the health physics laboratory. Okay. And that's the essential, those were the essential parts of the PM1. The PM3A, which was also built, designed by Martin, followed the PM1 very closely. However, the PM3A was a contained plant. It was pressurized water, as a number of these plants were, and as Walter explained, used highly enriched uranium-235. We were enriched to 93%. Unlike the early plants, which had plates or square boxes that held the fuel, we had tubes, and the fuel was put in the tubes as pellets, and then the water around the outside of the tubes were heated. This plant was also specified to be air transportable, but it was actually delivered to Antarctica by ship. And the Naval Nuclear Power Unit at Fort Belvoir, my unit, operated the plant, and I had 4 Army and no Air Force on my crew of 25. Walter, this needs to be changed. But the Army, through the AEC, the Army Nuclear Power Program, through the AEC, designed the plant with Martin. And Martin built and operated the plant until it was accepted by the AEC, but it was never owned by the Navy. It was always owned by the AEC. Why? After the 57-58 IGY year, International Geophysical Year, in 59, all the signatory nations that did scientific experimenting in Antarctica were called together by President Eisenhower, and they negotiated the Antarctic Treaty. And one of the provisions of the Antarctic Treaty was that there would be no nuclear waste in Antarctica and no military activity in Antarctica. And anything built in Antarctica would be open to every other signatory nation to come and inspect it. And at the nuclear power plant in late 63 or early 64, I had a delegation of Russians inspecting our nuclear power plant. Also, we had a Russian mechanical engineer exchange scientist over the winter who I became friendly with. This is a map of Antarctica. The location of the plant was right here on Ross Island, which was at the edge of Ross Ice Shelf. The Ross Ice Shelf was about the size of the country of France. It was the irresistible object moving toward the sea and calving off icebergs, and it backed up against the island, which was the immovable object, in huge pressure ridges of ice. Probably about 600 miles across the face of the ice shelf. Over here is Roosevelt Island, and between Roosevelt Island and the mainland is where Admiral Byrd had his 4 Little America stations in the 30s, 40s, and 50s. The South Pole is right here. The edge of the Antarctic continent is right here, about 800 miles into the PM3A, about another 800 miles to the pole. And due north is Australia and New Zealand. And our route for getting there was through New Zealand. This is a view of the PM3A. Again, the primary building was right here. In our case, because we were contained, there were 4 steel tanks buried in the ground, backfilled with crushed rock, and the 4 of these tanks had enough volume in them to maintain a maximum credible accident for that plant, and they were all interconnected. So one of the tanks held the reactor, the pressure vessel. This building was the secondary system, which had the steam, the steam-driven turbine generator set and the feed water skid. Down the end of that building, this was my office in this corner, and we had a lounge, health physics laboratory. This was our air-cooled condenser, if you will. You'll notice these large doors on the side. These doors would roll up a little bit as far as you wanted them. And in the ceiling, in the roof, were 8 fans. And with the air coming in underneath the doors, running across tubes of a condenser, and then exiting through the ceiling, through the roof, being drawn by those fans, was the cooling operation that we had. The low pressure steam from the turbine entered the tubes as low pressure steam. It exited as water. And occasionally, when the control room operator wasn't paying attention, it tried to exit as ice cubes, and the tube would freeze up, and that was a maintenance problem. back. This shed was just for storage of low radiation waste and that sort of thing. This building housed two 16-stage distillation evaporators, and with export steam from the turbine, we made all of the fresh water for McMurdo Base. This building on the ground floor was the maintenance shops, and on the upper floor was the shop stores, and we had 15,000 parts, individual parts, stocked in the shop stores to keep the plant operating and reliable. This building housed a CAT generator, so that generator was necessary to restart the plant. This is the late 50s, early 60s configuration of McMurdo. There would be about 200, 225 people winter over here, and there would be 1,000 people in this camp in the summer. Presently, it doesn't look anything like this. They're more modern structures, 3-story, flush toilets, showers, you name it. We had it a little rougher. My crew lived in this Quonset hut right here. I lived in one of these buildings, and this was our mess hall. Okay, let's see how we're doing here. This is the control room at the PM3A. This is the control room operator, and he monitored everything and controlled everything that was going on in the plant. There was an equipment operator that roved the floor taking instructions, and the shift supervisor that kind of watched them both. And then a health physics person who was taking water samples and that sort of thing and doing his job. The PM3A was delivered on the Navy transport, the Wyandotte. It was packaged up like this. Each of these packages were no more than 8 foot by 8 foot by 20 feet. That's what could be loaded into a C-130 Hercules aircraft, so the plants could be air transported any place in the world. Today, the site of the plant at elevation 300 feet on Observation Hill is a Antarctic Historic Foundation location. PM3A nuclear power plant, authorized and funded by the U.S. Congress, August 1960, designed and fabricated by Martin Company under contract to the AEC, erected by Navy Seabees, January, February 62, first criticality 4 March 62, operated and maintained by officers, Seabees, and hospital corpsmen of the Naval Nuclear Power Unit, Fort Belvoir, Virginia. Crews were augmented with Army and Air Force personnel, a few. The plant was shut down in September 1972, and in May 1979, PM3A decommissioning was complete, and the site was released for unrestricted use. The power was 1.8 megawatts electrical. We exported steam for desalinization. The plant, over its life, was available 72% of the time, which was not bad for the inhospitable environment we were in and the difficulty of getting spare parts and that sort of thing. Our record power run was 4,400 hours in 1971, and it's the only nuclear power plant to have operated in Antarctica. Okay. The Army had a plant similar to the SM-1 at Fort Greely, Alaska, which powered a missile site. The interesting thing to me about this plant was that the power was on, whoops, what did I do? There we go. The power was only 2 megawatts electrical, but 20 megawatts thermal. Alaska, heating. The plant was primarily there to heat the base. And it was at Fort Greely, Alaska. That plant was started in 58, went critical in 62, was shut down in 68. And it was also designed by American Locomotive Company. And it provided power for a missile site, if you will, defense. Picture of the SM-1A, it looked a lot like the SM-1 in Fort Belvoir. And there's where Fort Greely is located in Alaska. The MH-1A, this is the last plant that we talk about, is an Army plant. It was built in the middle of a Liberty ship, World War II cargo Liberty ship. The ship was cut in half. All of the propulsion equipment was removed. There was a nuclear power plant inserted in the middle of the two halves. They were put back together, and now it was a huge barge with a 10 megawatt electrical nuclear power plant in the middle of it. It was tested at Fort Belvoir, right 2 stones throw from my office, designed by Martin. The MH-1A Sturgis was the name of the vessel, provided electrical power and water to supplement Gattam Lake. It allowed 5 ships per day to use the locks, and it was deactivated in 1977. It was in the reserve fleet for a while. Right now, this plant is in the final throes of being scrapped in Galveston, Texas. And the SM-1 at Fort Belvoir is presently being dismantled, and the site will be returned to unrestricted use. This was an original concept drawing of the MH-1 as a barge. This was what it looked like down at the Panama Canal location. This was a console that was used at Fort Belvoir to train operators. And this is a view of the barge as it looked. The power was exported from this substation on the bow of the ship. In fact, you can see lines going down here. I guess they're waiting to pull the lines ashore. There was a conceptual plant after the ML1, the MM1, which was to be larger, truck mounted, and to follow Patton's army with all his tanks into battle. This never materialized, of course, because the ML1 and ammonia as a fuel didn't work out. This was another conceptual drawing of what it would look like being transported to some remote site. Walter, we turned it over to you. I used up a lot of our time. Well, I'm going to have to leave at 2:45 for Susan's appointment, so if there is a question or two that's burning, I'd be glad to answer them.
Any burning questions in here?
I'm resident here. I'm glad to talk to anybody anytime, too. Yep, let me get out of that.
Those of you on Zoom, we're just doing a mic change. We'll be right back with you in a moment. Any comments or questions in here?
Yeah, give me your wallet. I'll never mind this. Testing.
Mm-hmm.
Thank you very much, Will. I've told a lot of people that the first flyer never has a chance. I talked about going on a cruise to Antarctica, and Will said, I lived there. So, you have to be careful what you say around here because we have a lot of people who live here have done a lot more things than you have. Okay, Air Force Nuclear Power Program. 46, it was designed and set up pretty much like the Navy and the Army was. AE Assistant Director for Aircraft Reactors Branch. An Air Force Deputy Chief of Staff for Development of Nuclear Systems. Fairchild Engine and Aircraft Corporation did a study contract at Oak Ridge. And whenever you do a study contract for the military, your conclusion has to be, we need to continue this project. So they deemed it feasible. 51 GE company in Avondale, Ohio, was designing component test program for reactors, materials, and so forth. In 53, I don't know why I have unbold there, but in 53, the Secretary of Defense abruptly canceled the B-36 experimental flight program. And it's interesting that he said that you shouldn't create a proof of concept vehicle if it's not going to be an operational vehicle. And here's where Rickover jumped the gun and said, we have to put this on a submarine or a ship. You have to build it exactly like it's going to be on the submarine. And the Air Force was said, no, we just want to see if we can do it. So this was the Air Force crazy airplane that I mentioned that I would be showing you. And if you look over to the arrow pointing down to the cockpit, This is on the left is the lead-lined cockpit to protect the flyers from the nuclear plant that they were going to put back in the middle of the airplane. I always thought that was crazy. If it's not a submarine, who needs it? So they had a continuous airborne alert missile launching low-level penetration CAMEL program. You have to have fancy names in these military programs. Another reorientation, when they canceled the first one, you just change the name and you keep going. So in 61, JFK ordered a review of all the DoD projects and the nuclear rocket engines, Project Rover and nuclear ramjet, and we'll look at some of those. They were also crazy, I thought. Project Rover, nuclear rockets. I came to the University of Florida probably in the summer of 62 or 3. There was a program here at the university for studying how to make a nuclear rocket. And we were talking about thin films of graphite with embedded uranium to make the reactor. And if you blow hydrogen through it, that would be the moderator. And you would get a whole bunch of power out the back end. Kind of crazy. But they actually built some things. And this is one that looks like the hydrogen rocket engine with a nozzle. So it's not clear to me, but I'm pretty sure that while you were in the atmosphere, the hydrogen would ignite to get additional boost other than just the reactor heating the hydrogen and blowing out the bottom of the rocket. So here was the Kiwi Phoebus, space nuclear project, and they were building this nuclear rocket again to test it. And again, they were pumping hydrogen through it to make it go critical, to get the power out of it. And they would generally run out of hydrogen after running a few hours of testing because it really used a lot of hydrogen. But at one point, it ran for 12 minutes at 4 gigawatts, 4,000 megawatts, the most powerful reactor built at that time. So, and there's a new Air Force program because these programs just don't die. And this one looks like they're asking the Air Force to do what the Army did 30 years earlier, or 40 or 50. Small nuclear, portable nuclear power plants, microreactors, Project Pele. 2020, they funded for the microreactor project, a little bit of money. Corps of Engineers with the Army was going to be involved with the design and building of the sites. And then 2021, promoting small modular reactors for national defense and space exploration. Is my mic cutting in and out? Okay. Is this too loud? Okay, sorry. Small modular reactors for national defense and space exploration. In 2022, they had an environmental impact statement approved for the gas-cooled microreactor to be tested in Idaho. All this stuff was tested in Idaho because nobody lived there, and there weren't enough people in Idaho to say you can't do that. Now they're saying that, and they want Idaho cleaned up because it's a mess. Anyway, they're doing the environmental impact statement. So, detailed plan. 5 to 7 years of R&D, fabrication, assembly, testing prior to final approval. With 100 pages or more, hundreds of pages of the environmental impact statement, can you imagine how long design and construction of the Nautilus would have taken? I mean, Rickover was a take charge and march off kind of a guy, and that's what we did. Okay, here's Project Pele, a gas-cooled microreactor, and we talked a little bit earlier about the gas-cooled reactor. You have a reactor over here with gas going in and out, and it goes into another. It can be just gas or it can be steam, but this is a gas-cooled. It runs just like the turbine on an airplane. You have a compressor that compresses the gas and sends it back to be heated. In the airplanes, it turns on the jet fuel. And then the reactors, you run it through the reactor. It comes back out and goes I do that too. B for back. Okay. L for laser. Okay, so it comes through the compressor and through the generator or the power, whatever you're going to do with the power turbine. F for forward. Project Pele, there's their site out in Idaho where they're going to be doing and testing all of that. I do not know the current status of it. But now let's go to the Russians. The Russians had a nuclear-powered bomber, the Tu-95AL. The bulge after the wing where I put the arrow is where the nuclear plant was, and it's more than halfway back from the cockpit. Now, the Russians weren't as careful about radiation damage to people and equipment as the Americans were, particularly in the submarine service and the Army nuclear plants. So they just put the cockpit further forward, and it, apparently, as much as I know about it, it was not lead lined. Okay, Putin's nuclear-powered cruise missiles. We heard about that a few years ago, that he's got these nuclear-powered hypersonic cruise missiles, and he claims flight tests in 2017. The Pentagon says such a cruise missile crashed in the Arctic, and there was a big thing about whether it was scattering a nuclear radioactive waste there. And so to keep anybody from finding out about it, not much was said about it. And the International Atomic Energy Agency had a whole series around the world of online radioactive detectors to see if there's a problem. They were strangely all shut down at about that same time, and they did not, there are no published radioactive results from that. So nuclear projects in space, there have been a number of them. Will mentioned the radioactive thermal generators. I'll talk about that in a little bit. But dozens of satellites, mostly with radioisotope generators, and one reactor we put up in space. But the reactor was, again, making heat for radioisotope electric generation as opposed to steam generators or any of that other stuff, which you can't put up in space anyway. NASA and the AEC developed the so-called SNAP systems, the Space Nuclear Auxiliary Power Program, SNAP. We probably heard of that back in the papers years ago when it was first coming out. The Air Force operated some satellites with radioisotope thermoelectric or thermoisotope generators. I didn't find anything about it, but I'll tell you that I suspect that the CIA also has some satellites up there. Most SNAP systems were radioisotope thermoelectric. You know how a thermocouple works. It's two dissimilar metals that are welded together, and when they're placed in somewhere where heat is generated, they will make a little bit of electric voltage. And that's exactly how the thermocouples work in these thermoelectric generators. You have a whole bunch of thermocouples, and they're all connected in series and parallel, and each one generates a little bit of electricity, and you can bump it up in voltage by putting them in series, bump it up in amperage by putting those series into parallel. And these have been used around, the Navy has used some. It's very useful in a place where you can't make a generator. If you want a lighthouse on a remote island, you can use a radioisotopic generator and power up the lighthouse. And they're also used in space. The SNAP systems were also, some were fast reactors using thermoelectric or thermionic, the other kind of converters. And this is what one would look like. You have the core of the radioisotope, the radio generator, isotopic generator in the middle. And out on the periphery are thermocouples to make the thermoelectric conversion. But the thermocouples have to have a heat sink to get rid of things. So you have to have the hot thermocouple, the cold heat dispersant, and the electricity generated. So these are the way they look like. It's a heat source surrounded by thermocouples. And this is SNAP 27, left on the moon by one of our lunar explorers, and it's still up there. SNAP 10 nuclear reactor with thermoelectric generation. Only U.S. miniature reactor sent into space. Okay. The USSR has dozens of mostly reactor thermoelectric generators, particularly on their so-called ROARSAT satellites. They are radar ocean reconnaissance satellites with a thermionic generator. These, when they were first put up, really scared the heck out of the Navy because they were convinced that these were designed to detect where the aircraft carriers were. And the Navy created a bunch of operations where they would take an aircraft fleet of ships, maybe half a dozen or so. Like I told you last week, there's only two kinds of ships, submarines and targets. So the aircraft carriers are really big targets, but they would go out to sea in absolute radio silence. All the radios, all of the radars, everything was turned off. And they would watch the ROARSATs to see what the Russian reaction was. And they did take reaction. They repositioned their satellites to try to find the aircraft carriers because they were very worried about what the aircraft carriers were going out for. Okay. China has a lunar rover, and it had solar collectors and radioisotope heaters. It did not have the reactor for power generation so much as it was up there. A little bit of radioisotope production, but to heat the rest of the lunar rover. Here we go. RHU, radioisotope heater units, usually produce heat by spontaneous decay of plutonium-238. So this is the Chinese lunar rover. It has a lot of solar panels, but it has the radioisotope heat unit to provide heating for a rover, and I'm not sure exactly why they need heat, but it's very cold on the surface of the moon, and it may be necessary for some of the equipment to operate. Next week, woohoo! We're going to talk about commercial nuclear power plants around the world. This is a picture of the one in Crystal River, Florida. The nuclear power plant itself, the containment vessel is underneath the blue arrow. These heat exchangers over here are for the steam generating plants, which are over here. The nuclear power plant had a canal that came in from the Gulf, and they had their heat exchanger got rid of the heat into the Gulf waters, which was pumped back. And because that's a problem with the disturbing the ecosystem in the Gulf by heating up the Gulf waters, they had to do a mitigation. And what you see back here, these ponds are not for heat exchange, they are for a fish hatchery. And there was a big fish hatchery there. And you may remember a year or two ago, we had a series of ILR talks about the Nature Coast. And when we lived in Citrus County, which is where Crystal River is, they generated the term Nature Coast because we have the First Coast and the Emerald Coast up in the Gulf and the Treasure Coast, and we have all these other coasts. So it's a marketing name by the Chambers of Commerce from north of Tampa to up in the armpit of Florida. So anyway, they had to make a fish hatchery to compensate for the fish kill that might happen by using the Gulf water and heating it up. And I've toured both the reactor plant and the fish hatchery out there. And the current director of the Marine Science Station in Crystal River, which was built as a response to Sputnik, used to be one of the techs at the Marine Science Station. And they had a problem with the fish hatchery, like a lot of fish hatcheries do. There's a lot of fish there, and the birds come to eat the fish. And you're not allowed to use explosive, but you can buy, if you want to buy explosives right now for the 4th of July, which thankfully is already behind us, you have to go to one of these little stands and say you're going to use it for mitigation of birds in your farm or your fish hatchery or whatever. You have to tell a lie to get fireworks you don't need. But anyway, they had some dogs that they had out there, and their job was to just run around and scare the birds. But they tried to grow shrimp at one time, and it turned out that if you can grow shrimp, you can have a shrimp farm, but if you have any leftover fish in these ponds, they will eat all the shrimp before you can harvest them. So they quit growing shrimp. They did then grow other fish, and they would pump them out of the pond into a great big truck with a great big hose on the back of it, and they would back it up to a river somewhere where they're allowed to dump the fish, and they would dump all the fish out, and then they tagged a number of them so they could determine if they came from the fish hatchery or just were normal fish. So, and they weren't nuclear. They didn't glow at night or anything like that. It had nothing to do with the power plant. Okay, we're past time to finish, but let me just tell you about this nuclear containment vessel. It's about 3 to 5 or 6 feet thick concrete and reinforced steel. It was designed to accept a crash landing of the largest jet liner at the time, the 707s, and it works very well. Then Duke Energy decided they needed a new steam generator, so they cut a hole in the side of it, and they got the new steam generator in and other components they needed because the doors aren't big enough. And they put it all in there, and when they tried to restore the integrity of the concrete shell, they didn't get it restored, and it totally failed. And if you're a Duke Energy Power customer, I'm sorry, you're paying for that, because the stockholders are not. Enough said. Any questions? I'll stop and I'll entertain questions. And if you have a question for Will, you better ask it first. What? No questions? Oh, yeah. I didn't see your hand. I'm sorry.
I wanted to ask Will.
No, it's on. Just hold it right.
Okay. Will, did your family live with you in that Quasit hut?
Not accompany me to Antarctica.
Hold it right this way.
Try to eat it.
I think the question was my family in Antarctica with me? No, it was not. They were not. Back in the 50s and 60s, there were really no women in Antarctica, period. It took until after that before ladies were hosted at McMurdo Sound. My wife would have been glad to go, but it wasn't allowed. And I didn't have any women with me in Vietnam either.
Yeah, for Walter. So Walter, I don't know if you read The Martian or ever saw The Martian. But anyway, there was a scene in that with Matt Damon, and he's out on his rover freezing his butt off and remembers that from a previous landing, there was some buried nuclear core of some sort, and he realized and went and dug it up and stuck it in the back of his rover, and so then he had heat. So you were wondering what that was, what that might be used for. But so
It could have been possible, but it would be a stupid thing to do to put radioactive material
Right.
in your
Well,
backpack.
that was my curiosity is like, aren't you being radiated if you're doing that? But so I guess my question for you is, we're talking about going to Mars at some point and in not too distant future. So I was wondering what your thoughts were on what would be required to take with you to generate enough power to have operations on Mars for any length of time, and what the issues might be on Mars versus someplace here on Earth.
Well, we have the Mars rover up there now with solar panels, and the Viking 1 and 2, which were launched about 50 years ago on the mission to Pluto when it used to be a planet, and further out, they have radioisotopic generators. They are still generating. They have powered down the Viking 1 and 2 because they can't really collect data. They're out of the solar heliosphere. And so they're just floating off in space, but they're still reporting back after 50 years. I don't remember the half-life of plutonium-238, but it's in the order of, I would say, 1,000 years or more. And so it'll generate electricity for a very long time.
I have really dumb questions. All those nuclear reactors that Will talked about that were decommissioned, so what replaced them?
Which ones?
The ones that he was talking about?
Oh, in Crystal River, for example?
No, the ones that Will talked about. Did he leave?
Yeah, I'm not sure what they're going to do about that, but I'm sure they'll have some radioisotope generators, thermoelectric or thermionic generators to generate electricity. And if you keep building more and more of them, you can get more and more power. But that'll be one of their real concerns is what are they going to try to do and how are they going to power being able to do that?
Yeah.
So
Yeah.
can't answer any more than that.
Okay, one other question that since all these satellites have nuclear power, the Chinese one that came down 2 days ago, so that also had?
That would not have had, that was
Nuclear?
just that was a lifting rocket for the heavy segment of their space station. So it's just
Oh, it was not
uh,
a satellite.
probably hydrogen and oxygen and whatever else they use for reactor power, but it would not have been radioactive.
Okay, thanks.
Any other questions?
Okay, next time we will talk about the commercial reactor plants, and strangely enough, we will talk about the 3 Mile Island plant because it's a good nuclear power plant to talk about for civilian power production. We'll talk about the Chernobyl power plant because it was used in Ukraine and is still there. Several of them are still operating. And we'll talk about the boiling water reactors of Fukushima. And then the last session we'll talk about why all those had disasters and core meltdowns of one type or another. So that'll be our last session. The next one is on civilian nuclear power. The last will be about commercial or nuclear power plant disasters. And I'll tell you right now, all the ones for the United States Navy, 0. We're good.